All right, now this chapter is going to be the fun one. We have a pretty good thing going on here in terms of our simulation, but we can refine the look of the simulation a lot more in terms of adding more different sized pieces. Well, you'll basically see. I'll keep it a surprise. So, by changing our current wedge here, we can basically see which simulation we want to work on based on the different wedges. So this is still driving our regular simcache node here as well, in addition to the for loop where they're bringing them all in. Again, let's keep it at wedge 4, which reflects our new glue values, which I guess technically were the same as our old glue values, but never mind that. Let's fly up here to our Voronoi fracture. And I'm going to move this up to give us some room. So what are we going to do here? Looking at our fracture, there's some distribution of size. Like, these are kind of small, these ones are kind of big, but we can do better than that. Especially because there's a kind of a gradual, gradient from big to smaller to small to small, and then back up. It's kind of like, it still kind of feels blah to me. So what I want to do is I want to take some of those pieces, just randomly, and smash them up into much smaller pieces. So make a for each loop. And for each loop is running 100 times because there are 100 differently named pieces coming out of the Voronoi fracture. So that makes sense. And once we're in there, I want to sometimes switch over, and we did this in the first lesson. I want to sometimes switch over into some kind of subfracturing thing over here, where we'll scatter some points and we'll run a Voronoi. Now that switch needs to be based off of something. So we need to create a meta import node. And as we've seen before, the meta import node stores some detail attributes like what iteration we're on. And that's often the one that we want to use, and is in fact the one that we want to use now. So we'll go to this switch and we'll say something like, hey, maybe, oops, didn't quite make it there. So let's go get that attribute and say for each metadata, grab the iteration, and 0 because it's not a vector. And we know that that's going to return us some integer, and we don't want to switch to that integer because that could be something from 0 to 99. We want to make a random number generated off of that. And let's also just add in like some random number here to differentiate it from other random calls that we do. Just by changing that incoming seed, we'll get a different outgoing random number. So this will get us a number, between 0 and 1, a float, but we still need to have, we want our output to be 0 or 1. Are you going to take input 0, which was the original piece, or are you going to take input 1, which is our newly subfractured stuff? So with our random result from 0 to 1, let's simply compare that to some value between 0 and 1. So I'm going to say, hey, are you greater than 0.6? It will be greater than 0.6 40% of the time. So now, if I were to, let's say, go into single pass mode on here, watch the input here, you'll see it's switching at different values. So at different iterations, which are the same as the different passes, 40% of the time, it will choose this input, something like that. So right now, that doesn't mean anything because it's not doing anything on that side. So let's have it actually do something on that side. And I hope this was clear that by saying greater than 0.6 is 40% of the time, because remember, it's returning a number between 0 and 1. So if it's evenly distributed, 40% of the numbers between 0.6 and 0.1. Cool. So here's an example piece, which is actually the last iteration of the for loop that's showing us. We want to scatter some points there. And we don't even need this null anymore. We want to scatter maybe something around 3 points. Let's say 2 to 4 points we would want here. And the actual position of those points is dependent on this global seed, as we've seen before probably as well. it doesn't matter what number we change it to. It's not some, slow ramp or noise function. As long as this number is different than any other number in the global seed, you'll have a different distribution. So just put some number in there. And now we need to do another random number based on what iteration we're on. So we already know we want this. We say rand based on the detail. Again, the same exact thing. For each metadata, iteration, 0. So that gives us a random number between 0 and 1. But we want to remap that with a fit 0, 1. Let's remap that to 2 to 4. Cool. So now if I were to look at this whole thing, we're going to have some of the pieces will be replaced by little groups of points. So we know it's working. So come back in here, make a Voronoi. We'll just take the original piece, which was this, take the original piece, put that into the Voronoi fracture based on those points. And now if we visualize that, we have 3 sub-pieces. Altogether, we have this. And I'm going to say, let's turn off this for a second. These are our new pieces here. Cool. Now, that's progress, but I can already see a little issue here. See that kind of black area? That's a normals problem. And that can happen anytime really making new geometry or fracturing geometry and stuff. I would say the easiest way to fix that is dropping a divide SOP down. And the reason why is these are strange polygons. These polygons are more than, we're used to quads, 4-sided polygons and triangles usually in geometry. These are what we call n-gons. They have an arbitrary number of sides. And that's valid, but it can cause issues with fracturing stuff. So by putting a divide down here, we're going to force it to triangulate it. It won't make any new pieces, it's just going to triangulate the pieces as they are. And now you'll see on the other side of this, there's no problem anymore. So there it is with it off, there it is with it on. Great. So that's no problem. And I would also say that it has this smooth look here. I kind of want that bevel to have a sharp edge. So let's make some normals on it too. Now that we've calculated all our pieces, it'll make the cusp angle like super low. Cusp angle is basically saying if the angle between 2 polygons is greater than this number, cusp it, meaning make vertex attributes, normal attributes, saying that this polygon's pointing this way and this polygon's pointing this way. I mean, you can see the results. It goes from being smooth and weird to being sharp and nice. Cool. So let's just hook that back into our ongoing procedural thing here. We kill the visualization as always. It computes the new connectivity. So before it went from 0 to 100, now it'll probably go down to something higher. It looks like 0 to 178, so that's like 179 pieces. It's going to name them that. Name piece 0 to 178. And when we assemble them, we do indeed have 179 pieces now. We can view them here as well. See, now we have these pockets, all these cool little pockets of little pieces, really small ones here and there. That'll look a lot nicer. So that also means we're going to have to update our business over here. We certainly don't want that poly bevel anymore. Let's write out these pieces, and everything will still work here. The file cache is going from 0 to 178 now because there's 178 pieces. They're all named. Everything's great. So I'm going to say let's write out new instance versions. I don't even remember which one we were up to, so I'm going to go up to 5 to make sure that we get it. And that's going to be, this 5 here. So let's write out these pieces. Save the disk. There we go. So they're all written out. So now the next time we do our sim, it'll be ready to take them. Cool. All right, and speaking of that simulation, everything else should be flowing down fine too. So if that is that wall, the wall becomes the building, or becomes the room, becomes the building, and all that jazz. In particular, I'm interested in seeing the new connectivity, or rather the new constraints. You can see kind of those little clusters, these little dark areas of the new pieces, but that's it's what to be expected. Let's just go ahead and see what this looks like. Let's see what this sim looks like with our new glues, meaning the old glues, and all those new pieces. So we have 79 pieces. So there's more, significantly more than we just had. So it'll probably take a little longer, but hopefully not too much longer.